Hello everyone, this is Yinfei from Apple AI/ML. Today I'm going to talk about the recent progress on learning visual and vision language models with noisy image text data. It is an emerging direction and lots of great work came out in the past 2 years. So I will split the talk to multiple sessions. First to talk about how do we scale up the dataset, where we can find a good amount of the image text data. And secondly, I will talk about the contrastive learning using the noisy supervised signals. Then the multitask learning and the generative models. At last, I will try to summarize the topic and list some of the promising directions, but not listing the sections above. First, scaling up the noisy image text dataset. So in the recent years, we have seen model sizes continuously growing with larger scale of the training data. And the scaling both data and the model sizes has been shown as a critical factors for pushing the limits of the model quality in vision or language models. For example, in the NLP community, which often uses large-scale datasets like C4 contains 150 billion tokens to train large language models. In the vision community, there is also similar effort like GFT data. However, when looking at the vision plus language models, it is less straightforward to get image text data like a pure image or text. The size of the image dataset could be abound to train large-scale vision and language models. In order to solve this problem, the community started looking at the data from the web, the secret source for image and text. It is called secret because people often think the text surrounding the image is too noisy to be used as a supervision signal. However, recent work demonstrates this is actually a great resource to train such models. This is an example from Wikipedia page. There are a lot of different fields surrounding to an image in the web. And for example, the title, alt text, description, and maybe the closest text from the other fields as well. Among these fields, alt text has been the most commonly used and relatively most clean text as well. To my best knowledge, the use of the alt text data as a source for training in image text models can be tracked back to 2018 in the work of the Conceptual Captions dataset. But at that time, people still do a lot of the heavy processing and filtering to clean the data. So the first version of the Conceptual Captions has only 3 million examples. Until 2021, Align model released most of the constraints and only keeps the light filtering steps. And we start getting billions of the image text pairs then. The other fields could be useful too. Title text quality is slightly worse but close. In some work, I saw people combine the alt text and the title if they want to use even more data. Description is slightly different. It often contains the information beyond the image. It will create hallucinations if you just train the model naively, but they can also be useful in some applications. For example, when combining the extra features or the external knowledge. Now we talk about the cleaning step. Actually, the people's intuition is right. The raw data are really noisy. So we need to do some processing to clean it up. However, because the data scale is large, the processing needs to be simple, so it can be scaled. Some common heuristics people used to process the data at the image side, for example, to remove the not safe for work images or remove the images which either too small or with irregular shapes. And sometimes the images associated with too many text could be some icons or common images that are not meaningful. On the text side, people also filter out those over-frequent text, alt text. Examples like image sizes or common kind of, for example, image.png. And people also like to remove those text contains real words or the text too short or too long. These simple rules could maybe filter out maybe 80% or even 90% of the data, but because the original size of the image text data we have in the web is really huge, we still get a large amount of the data can be used to train the models. How many of them? And this picture shows a what the community has achieved in the past couple of years on scraping image text data from the web. It is like a exponential growth, and now the image text data we have probably enough to support the model development for next several years. Well, hopefully, the development on the modeling side are also incredible. So maybe in next year, people find that we need even more data to train the best models. And some of the examples of the processed data from Align dataset, we can see that they are still noise. For example, in the second image of the first row, you can still see the alt text thumbnail for version as of blah, blah, blah. It's not really a good description text. And of course, there are still room to improve this dataset and the models by keep cleaning the data. But it already good. It is already a good start to train large scale models. Now with the data, we need to think about what model is a good start. And people choose contrastive learning to learn from such data pioneered by CLIP and Align models. The contrastive learning approach has been very popular in the last couple of years for either pure image tasks or pure text tasks. It is a data-efficient approach and it can be scaled up easily. The benefit comes from that the image and the text are modeled separately in image contrastive learning framework, and the negative examples can be also sampled very efficiently. Another intuition of using contrastive learning for image text training is that we can treat the task as a caption or text prediction task from the image. And it has also been proven to be an effective approach to learn the vision models in the past. Maybe some of you are already very familiar with the contrastive learning, but let me still give a brief introduction. In the contrastive learning framework, it usually employs a dual encoder architecture, which encodes text and image separately, giving in a training batch. Then apply matrix multiplication on text and image encodings. The diagonal elements are treated as positive and the other elements are treated negatives. A softmax is applied for each row to predict the positive element. One free benefit we get from the contrastive learning, as I said before, is a lot of the negative samples. And not only from the local batch, but also from the other replicas, especially when using a distributed training. More negatives has been proven to improve the performance in many contrastive learning tasks. After training, the resulting models are good for text-image search, image plus text to image multimodal search, and also the zero-shot, we call zero-shot classifications. Some of the examples also from the Align paper, we can do the multimodal search and the text image to text and the text to image retrieval first. Given an input text, the model is used to retrieve the closest image in the embedding space from a very large candidate pool. In the first row, it shows the closest image from the candidate pool for query Van Gogh Star Night details, and the query Van Gogh Star Night in black and white, and Van Gogh Star Night on a canvas, etc. The model is able to recognize the differences of them, very subtle differences, and retrieve reasonable images. Similarly, the closest images for queries Lambert Street, view from bottom, view from top, bird's eye view, and in a heavy rain. And I would like to give a more example on the image plus text to image search. Motivated by the famous example previously when the word embedding was developed, king minus man plus woman equals queen. It was a very famous formula, and it allows us to use a vector or semantics to work with analogies. Interestingly, we can also observe the similar scenario in the joint image text embedding in space, actually, which learned from the contrastive learning. In this particular case, it is the Align model. For example, when we use a panda image plus a word red, we can retrieve a red panda image. Well, it's maybe not exactly the kind of things we want, but it's semantically close, right? And the last two rows also show the examples of the manipulating the colors and other attributes of the objective images. This attribute will be very useful in real applications for example, product search, when you want to search for something but with a different attribute, for example, a clothes in a different color. And at last, this type of the model enables zero-shot classification by turning the image classification problem to a retrieval problem. Some people also call it open vocabulary classification. And to my best knowledge, this was only enabled by the kind of most recent contrastive learning in work. And it has been used in the follow-up works to solve the unsupervised segmentation open vocabulary detection tasks in the recent years. The last page of this section, I want to discuss about the data efficiency versus model efficiency problem. Data efficiency means the quality of the data, clean, noise, information, content from the data. And the model efficiency indicates how well the model can learn from the same quality or same amount of the data. Some experiments from Alan clearly shows the larger model can benefit more from large but noise datasets. So this actually is a conjunction that the data size increase, even it is noise, but it may still a very good source for training the recent effort for developing foundation models. Now, at next section, I want to talk about the multitask learning. Why? So let's start from some limitations of the warp scale data. Of course, it is noise, as we discussed from the beginning. But there are also other issues like multilingual and data distribution. Strictly speaking, multilingual is still, or it is also a distribution issue, but let's still talk about it separately. First, multilingual. Assume we want to build a multilingual image text embedding space, which is very practical in the real-world applications. One option is simply scrape the multilingual image text data from the web to train a model. However, the truth is that the image text data scraped from the web is very biased to those top languages. The distribution is highly skewed, and more than half of the data are from English. And probably about 90% of the data are in top 10 languages. So for those languages that has very little image text data, what do we do? And the idea is we can consider actually borrow the data and the task or some ideas from the language learning community. For example, translation community has been working on the multilingual problem for decades. The Leipzig model developed in 2021 by Xiaoyu has been trained on more balanced by-text pairs with a contrastive learning objective as well. Considering it is also a contrastive learning objective, it is very intuitive or natural to combine the Leipzig model training with the image text contrastive training. So combining the two can largely alleviate the language bias issue, and the resulting model called Mural achieved a very large improvement compared to the other SOTA models. The model Mural is done by Ashley Jian and others at 2021 as well. Then talk about the image data distribution. I have been seeing in many papers arguing that the current pre-trained models does not work for their domains because of the distribution mismatch. For example, the e-commerce pictures. And multitask training, for example, the sleep model provides a solution for this by co-training the contrastive learning task with the self-supervised learning methods like SimClear, MSCOCO, or BYOL, and BIT, etc. Of course, there are more recent work exploring different combinations of the contrastive learning with the other tasks, or even unifying them. For example, the recent work Pali actually unifying all the tasks to a language model for the generative model task. I cannot list them all here, but looking forward to seeing the more development in this direction. We have several minutes left, so let's also talk about the generative models first. Image to text generation models. This field also experiencing the similar trend in past few years, starting from the Vortex model back to 2020, which was a trend on 100,000 MSCOCO training data. And then SimClear, GIT, COCA, and Flamingo models becoming larger and larger, but also much more powerful. I especially want to highlight the Flamingo model with pre-trained image and language models, and then combining the image and the text training. It achieved a very impressive human model interactive experiences. I definitely recommend to check it out if you haven't. Similarly to the text-to-image generation models, which is one of the hottest topics recently, or maybe not one of them, the hottest topic now, starting from the DALL-E model at 2021, and in less than 2 years, much more larger models have been trained on more data, and they comes out very quickly, like a DALL-E 2. Imagine Party and the recent the Stable Diffusion model, and even the text-to-video generation models. This direction is just actually developing incredibly. And in this slide, and we also see the similar trend, comparing the noise versus clean data for the text-to-image generation task. Small clean data, some observations is that small clean data is enough for generating high-quality images, and the web-scale noise data assign rich semantic coverage to the model. The rich semantic means even for the real semantic informations, like for example Superman or some characters from a movie, can be you can find the meaningful generations from this large text-to-image generation model trained on the large-scale noise web data. And the other side is actually from the generation examples from Party, the model size matters on both of the quality and the semantic coverage. We have talked actually the image to text generation task. And now back to the point I talked previously that the contrastive learning approach is very effective for learning from noise data. I want to discuss it here and compare the model intrinsic properties of a generative model and the contrastive learning models. For example, assuming in the noisy data, we have one text associated with many images. In contrastive learning, because the model is forcing the image to be close to every text it associated with, and that means it needs to be placed in the middle ground of all of this text, and just like a distribution matching. So if there is another text example like T2 here, which is more close to the I2, and is more likely the distance between T2 and I2 will be smaller, means closer, comparing to the distance between T1 and I2. But in contrast, in the generative model, if we have, for example, all 5 images is trained to generate the same caption T1, and there is only one example from I2 to generate T2, the model probably will learn to generate T1 for most of the time, just to be safe, because he find every time it generates the T1, it gives it was given a good reward, the positive reward. In real scenario, exact same text repeated frequently can be filtered out easily, but how about the same type of the text? E.g., for example, physical addresses and their images for real estate websites. So this is something actually we observed, some intrinsic properties for generative model and contrastive models. And the different properties will also lead to a different use of the data. And in some of the previous work, people also use this contrastive learning as a filtering stage or boosting stage. They first train a contrastive learning model from the noise data and use the contrastive learning model, the resulting contrastive learning model, to filter out the original noisy data, and then use a cleaned version to train the generative model. And people find that after the first stage cleaning, the model performance will be improved significantly. I think I remember the experiment was done in the translation community, but I think there are more to play with here. So the end of the slide, as a summary, so we talked about the scaling up the image text dataset from the noisy web scale data. In particular, we have talked about the image and alt text dataset, the other field, captions and descriptions, or even, for example, entities mentioned in the same page of the image could be useful. And we talked about the contrastive learning and the multitask learning are effective to learn from noise data. And in just actually the previous slide, I also talked about some of my thought and the intrinsic property differences between the contrastive learning versus the generative model. But the generative model are emerging too. Even actually, it's kind of maybe relies on higher quality data compared to the contrastive learning, but the recent progress shows with improved model efficiency, they still can learn very strong models from the noise data. But that's not all. We still have some downside of learning from the web scale data. For example, the ethical considerations, not safe for work images, biases, etc. There are a lot of discussions about the bad content from the lion images. And even I think there are some privacy concerns, some PII information may be disclosed from those datasets. But I still think this will be a very promising direction, and people will address these issues very soon. At last, I want to emphasize that we definitely have more to expect from the web. There are a lot of things we can mine from the web and we can learn from the web. I would definitely looking forward to seeing more directions from this direction. And at last, thank you everyone, and thank you for listening to my talk, and looking forward to see you offline and have more thoughtful discussions. Yeah, thanks.